Hello everyone and welcome to section 3 of unit 5. This is our third and final section of this unit covering the Pythagorean Theorem, writing our answers in simplest radical form, and the Pythagorean Inequalities. You should have already worked with writing your answers in simplest radical form at some point in the past, but in case you haven't, we're going to review that and the refresher will be good for you anyways. So we have, right here it says we can rewrite a radical in a form we call simplest radical form. To do this, we rely on the product property of radicals that states that the square root of x times y, and I'll zoom in on that, is equal to the square root of x times the square root of y. In other words, that's like saying that 8 is equal to 2 times 4. So you take something and you split it into two smaller pieces that have the same value. So we can do that with our square roots as well. So that means that we can break our square roots into the following multiplication problems. So for the square root of 20, I can say that 20 is equal to 4 times 5, and both of those would be written under the square root as well. So then 27 can be split into 9 times 3, and 44 can be split into 4 times 11. And again, I'm writing them under the square root because we're breaking down a radical. And the square root symbol is called a radical. Alright, so next it says, however, our goal in doing this is for one of those multipliers to be a perfect square. This will allow us to break it down even further. So if I take 4 and 5, because I already found perfect squares, the square root of 4, that's a perfect square because it breaks down into a whole number. So for 20, I have this split into the square root of 4 times the square root of 5, and the square root of 4 breaks down to 2, so I have 2 square roots of 5, and that is simplest radical form. So for 27, I have this split into the square root of 9 and the square root of 3. The square root of 9, it's again a perfect square, so that breaks down into 3 square roots of 3, and that is simplest radical form. Then for 44, we have the square root of 4 and the square root of 11. The square root of 4 is 2, so I have 2 square roots of 11. Alright, let's take a look at example 1 here, where we're going to just practice that a little bit more. So example 1 says to write the following in simplest radical form. So I have 28, and I can split 28 into 2 and 14, but neither of those are perfect squares. 4 goes into 28, and that goes in 7 times, so that's the one that I'm going to work with, because 4 is a perfect square. So I have the square root of 4 and the square root of 7. The square root of 4 simplifies down to 2, so I have 2 square roots of 7. Next I have 45. 9 goes into 45, and that's a perfect square. So I have the square root of 9. 9 times 5 is 45, so the second one would be the square root of 5. The square root of 5 is not a perfect square, so that's as simple as we can go. So I have square root of 9 is 3, so 3 square roots of 5. And then last but not least, we have the square root of 50. I know 5 and 10 go into 50, but those aren't perfect squares. 2 and 25 go into 50, and 25 is a perfect square. So I can say 25 times 2. The square root of 25 is equal to 5, so I have 5 square roots of 2. And that is a refresher on simplest radical form. All of our answers are now written in simplest radical form, and it usually will look like this. Now, if you have a perfect square as both of these things, then you probably have a perfect square up here too. Simplest radical form of a perfect square is just the whole number. If you had a number up here that couldn't be broken down, then simplest radical form would just be the radical of that number. For example, 17 is a prime number, so if we had the square root of 17, then we wouldn't be able to break that down because 17 is prime. Alright, now that we have taken a refresher on simplest radical form, we're going to go ahead and remind ourselves about the Pythagorean Theorem, which we've already used a little bit this year. Now the Pythagorean Theorem says a squared plus b squared is equal to c squared, and it only works for right triangles. Alright, so now let's take a look at solving using the Pythagorean Theorem and writing our answers in simplest radical form. So I have one example here, example 2, that says to find the missing value of the triangle below and to write your answer in simplest radical form. So I have 2 squared plus 6 squared is going to equal my hypotenuse, which is c squared, or in this case, we have x. So I have 2 squared plus 6 squared is equal to x squared. 2 squared is 4 plus 6 squared is 36 is equal to x squared. So I have 40 is equal to x squared. I'm going to take the square root of both sides. I want to write my answer in simplest radical form, which means that I'm not trying to find a decimal there. I'm going to break this down and see what I can simplify this into. 4 goes into 40 10 times. That will work. So I have the square root of 4 times the square root of 10, which means that x is equal to 2 square roots of 10, because the square root of 4 is equal to 2. And that is my answer. Alright, so just another refresher. We have something called a Pythagorean triple. A Pythagorean triple is when 3 non-zero whole numbers, a, b, and c, are in our Pythagorean theorem, such that a squared plus b squared is equal to c squared. So what that would mean is if we solve this out in the square root that we're left with at this step, if that was a perfect square, then we would have a Pythagorean triple. Common Pythagorean triples are 3, 4, and 5, 5, 12, and 13, 8, 15, and 17, and 7, 24, and 25. If you're ever solving a problem and you have 2 of the 3 of these, the third one has to be the third side, so you can solve knowing that it's a Pythagorean triple rather than walking through the whole process. Alright, so we have the Pythagorean theorem. I don't know if this one has been brought up too much before, but we also have the converse of the Pythagorean theorem, which says that if a squared plus b squared is equal to c squared, then the figure is a right triangle. So if you're not sure if it's a right triangle or not, but you know the side lengths, then you can plug it in the Pythagorean theorem, and if it checks out, then it is a right triangle. So let's take a look at an example. So I have example 3. Determine if the triangle with side lengths 7, 9, and 11 is a right triangle. So I have 7 squared and plus 9 squared, and I'm comparing that to 11 squared. 7 squared is 49. 9 squared is 81. 49 plus 81, 9 plus 1 is 10, carry the 1, so I have 9 now. 9 plus 4 is 13, so I have 130. And 11 squared is equal to 121. 130 is not equal to 121, so therefore this is not a right triangle. And it says, what if it doesn't work out? Well, it didn't work out, so this isn't a right triangle. That's what happens. If it doesn't work out, it's not a right triangle. If it does work out, if they are equal, then it is a right triangle. So this is no, not a right triangle. Alright, so not only can we determine if our side lengths form a right triangle, we can also figure out if they form an acute triangle or an obtuse triangle, because we have the Pythagorean inequalities. If a squared plus b squared is less than c squared, then the triangle is obtuse. If a squared plus b squared is greater than c squared, then the triangle. If a squared plus b squared is greater than c squared, then the triangle is acute. Another way to look at that is if c squared is greater, the triangle is obtuse. C squared is smaller, triangle is acute. If c squared is smaller, then the triangle is acute. If c squared is equal, then it's right. So if it checks out, if it's equal, right. C squared is greater, obtuse. C squared is smaller, acute. Alright, let's take a look at a couple examples. That's all that this is saying right here. So we're not going to go into those details. Example 4 says to tell if the measures... Tell if the side length measures is what we're really looking at. 5, 7, and 10 can be the side lengths of a triangle. If so, classify the triangle as acute, obtuse, or right. So I'm going to take my two smallest sides and I'm going to add them together. I have 5 plus 7. If 5 plus 7 is greater than 10, which it is, because 5 plus 7 is 12, then this checks out. It is a triangle. Yes, they form a triangle, and the triangle is, now we're going to classify it. So I have the possibilities of acute, obtuse, or right. So if I take my two small sides, I'm going to compare them again. So I have 5 squared plus 7 squared, and I'm comparing that to 10 squared. 5 squared is 25. 7 squared is 49. We're going to add those together. 9 plus 5 is 14, carry the 1. 4 plus 2 is 6, plus 1 is 7, so I have 74. And 10 squared is 100. And 100 is greater than 74, so c squared is greater, which means the triangle is obtuse. Let's take a look at another example. Example 5 says, tell if the measures 8, 12, and 14 can be the side lengths of a triangle. If so, classify the triangle as acute, obtuse, or right. So I have my two small sides, 8 and 12. 8 plus 12, if that is greater than 14, which it is, that checks out. So yes, they form a triangle. And the triangle is, now we're going to classify it. So if I square the two small sides and find the sum, if that is less than c squared, it's acute. Sorry, if this is greater than c squared, it's acute. If it's smaller than c squared, it's obtuse. So I have 8 squared plus 12 squared, and I'm comparing that to 14 squared. 8 squared is 64. 12 squared is 144. 64 plus 144 is equal to 208. So 208. 14 squared is equal to 196, which means that a squared plus b squared is greater than c squared. In other words, c squared is less, which means that this triangle is acute. And this is your answer. And same thing up here, that sentence was your answer to the question. And this amount of work and this amount of work is the minimum that you should be showing me when you're trying to show if a triangle can be formed and what kind of triangle it is. Alright, that is it for Unit 5. We will not be taking a test on this unit, but all of the information in Unit 5 is going to be on your semester exam. So you can expect that it will be there. We'll be doing some review before then to get some extra practice in, and you will still have your mastery check for 5.3 as well.